Assalamu alaikum warahmatullah. Welcome to the second lecture of our mechanical vibration subject, and in this lecture we are focusing more into the mechanical vibrations. In the last lecture we discussed what the system dynamics is, and we studied what do we mean by system, how to classify them, and what does it mean by dynamics and dynamical system. So just to relate between the last lecture and this lecture, system dynamics, I will just call it SD, can be applied on mechanical systems. It can be applied on electrical too. It can be applied on fluid system. It can be applied on thermal systems. So you see, system dynamics is basically a technique to study the changing behavior of any system with the time. And you can study anything, maybe a surge in electrical consumption, increase in current consumption, maybe the resistance to the flow because of the valve that is attached here, because of some heat conductor, and the air is blowing over a heat conductor, so how quickly the temperature will rise up of this air from 25 to 50 degrees centigrade. So you see, all of these are examples of changing the state of a system with the time. So the system dynamics technique can be applied on any of these systems. So our subject is mechanical vibration, which is one of the application of system dynamics, that is the mechanical vibration. And the fundamentals of approaching the solutions of mechanical vibrations, or to perform the analysis of a vibrating system, is the same. Obviously it depends on system dynamics, so the fundamentals steps are same. So now, starting with the mechanical vibration, what vibration is, or it is also called as oscillations. So any motion that repeats itself, any motion that repeats itself in an interval of time, is about a mean position. You can add about a mean position, or it doesn't need to be about a mean position as well. So in an interval of time, it's called vibrations or oscillations. So although they both are same, vibration oscillation, sometimes there's a minor difference. They're used in different meaning. The oscillations are fixed motion of a body about a mean position, while the vibrations can be a uniform oscillations, or it can be a random vibration. So what does it mean? If the system is moving equally about a mean position in an equal interval of time, we call it oscillations. That's oscillations. While the vibration can be oscillation, it can be random as well. Let's say this one, although it is also vibrating, but it doesn't have any fixed pattern. Although we will study how we can find out a fixed pattern out of such random vibrations. So there's a specific technique for doing that. So that is just a basic introduction of what the mechanical vibration is and how it connects with the system dynamics. Now, jumping towards a vibrating system. So, to classify this vibrating system, or to understand today's lecture, we will be focusing on what the vibration and oscillations are. We have discussed that one. Then the second thing, we need to understand what are the elements of vibrating system. What makes a vibrating system, mechanical vibrating system? And then we will further find out how we can classify different types of mechanically vibrating systems, with the additional topic of degree of freedom. So starting with the second section, that is elements of vibrating system. So there are three fundamental elements of vibrating system which makes up a vibrating system. That is, the first one is mass, or you can call inertia, the property because of the mass. Second one is spring, or the stiffness, that is a property because of the spring. And third one is damper, or the damping itself, that's a property because of existence of damper. So two of them are compulsory, these two, they are compulsory one. And this one, it can be present, it cannot be present in some cases, although the, in reality it's always there. Like it's always there for real systems. But theoretically we can add and we can remove the damper or the damping out of our system. So what do we mean by the elements of vibrating system? So if we see what's happening in the vibrating system, sorry, let's remove this one. So what's actually happening in the vibrating system? uh, Vibrating system or the mechanical vibrating system is nothing, it's simply invisible, you can call dance. It's an invisible, I'll just explain it metaphorically. It's kind of invisible dance between potential energy and kinetic energy, and I will explain how, what does it mean by. It's kind of invisible dance between the potential energy and kinetic energy, and they will keep on dancing like this. Only the one to destroy the party would be the damping. It's like a destroyer of the party. I'm just explaining it metaphorically, right? So the mechanical vibrating system is basically, it's a combination of interconversion of potential energy to kinetic energy and kinetic energy back to the potential energy, and this is what makes a system to vibrate. And only thing that slowly decay this dance and ultimately make sure that the system uh, achieves or becomes or stop vibrating, that is damping. So what do we mean by here, this dance of potential and the kinetic energy? So if we go here, let's assume this is example of, yeah, okay, example of a mass. In the last lecture we discussed example of a car. If you remember, a car which has hydraulic system, we were modeling that one. So let's assume this m is the mass of the whole car, and below, under the car body, you have the springs, that's let's assume that the spring combine is a combined representation of tires plus hydraulics, right? Because the main purpose of hydraulic is, let's say, if the car is going from the onto a bumpy road, uh, onto a bumpy road, so with every bump it will experience a force, right? Because the road is not even, so with every bump it will experience an excitation force. You can call it excitation force. So because of this excitation force, this spring will absorb this force, right? And we know the spring is capable to store the potential energy. So the first element from where the mechanical vibration start is spring or the stiffness. It stores potential energy. And by spring we don't mean that there should always be a spring physically present there. Means like a spring like behavior, maybe there is kind of a any compressible solid body which is capable to absorb the force or the pressure and then release it. So what does a spring do? So if you apply uh, pressure onto a spring, it will be compressed, and once you release the force, it will go back to the original position, right? This is what a spring does. So going back to our car model. So because of that, once the excitation force, because of the uneven road, uh, it acts onto the car, the spring, which is a combination of tire and the hydraulics, let's say, absorbs that potential energy. And as soon as that force is removed, let's say now this road is even, as soon as that force is removed, that spring releases that energy. This is what the spring does. Which if you apply force, it will be compressed, and as soon as you remove the force, it will release that energy. So that potential energy will be converted into the kinetic energy, right? And there comes a second element of the vibrating system, that is mass or inertia, you can say, because the inertia exists because of the mass. So when this potential energy has been converted into the kinetic energy, So and this makes sure that the systems keep on moving because the inertia is what it opposes the change in the state or the motion of the body. Let's say kinetic energy is equals to half mv square. So this mass tries to make sure that the system keeps on moving with the constant velocity. It opposes the acceleration. By acceleration I means either increase or decrease, both acceleration or deceleration. So the mass brings the inertia, and what is inertia? Inertia that changes the that makes sure if a body moves, it tends to move with the same momentum, and if it stops, it tends to retain its shape. This is what inertia is. So whatever the state system is in, inertia tries to maintain that shape. Is it? So this is what the mass is going to do. So and once the kinetic energy reaches minimum, it will convert back that into the potential energy. The more uh, the more clear example would be if you see the wall clock again, and wall clock has pendulums, right? Let's say now at pendulum you apply this force here. You apply the force here, and because of that now the pendulum start vibrating to this extreme position, and then coming back to this extreme position, right? So when the pendulum moves here and reaches this extreme position at this point, let's say call it x positive, call it x negative. So at this point or this point, at both of these, for a moment of a time, for a fraction of time, the pendulum will stop. And because this was the original height of the pendulum, h1, now the height is this one, h2. So because the height here is more, so naturally the potential energy will be more, mg h2 minus h1. So at this point or this point it has a maximum potential energy and the kinetic energy is zero, because what happened, you applied the force, and because of that force the pendulum went up and reaches the maximum potential energy. Now it has reached a maximum potential energy, and now the force has been removed. What will happen naturally, it will release that potential energy, and it will tends to go back to its original position. And as soon as moving towards the original position and it reaches here at this particular point, because the potential energy is minimum, becomes zero. And let's say h1 is zero, let's suppose. And the kinetic energy, because at this point the velocity will be maximum, so it is maximum half mv square. And because of the inertia, because of the mass of the pendulum and the inertia will try to maintain the velocity of the pendulum. So that inertia will make sure that pendulum will go back to the other extreme point. And again, once that reaches that extreme point, by the time the kinetic energy has been transformed into the potential energy. And again, at this point kinetic energy is zero, and because it has reached the maximum potential energy, and now the kinetic energy is zero, so it means there's no effect of mass inertia, which itself is a force. So now the potential energy, it will release the potential energy and it will go back to its original position, and this continues. So this invisible dance will keep on continue for infinity. When it will stop only when there's a third one, which I call the destroyer of the party. So what the destroyer of the party is, maybe there is some uh, connection, nut or bolt, which is not very lubricated, or there's air here that is resisting the movement of the pendulum. So here that nut or the bolt connection or the air, that is a damper, that is a damping effect in this case. So that will slowly make sure that in the next swing the pendulum don't reach the maximum. One pendulum reaches here, then in the next go the pendulum maximum reaches here, in the next one, and slowly and ultimately it will stop moving. So this is what the mechanical vibrations are. So as I said, like it's a kind of invisible dance between the potential energy and the kinetic energy, and it will keep on changing from potential to kinetic energy. This makes sure that the system keeps on vibrating. Only thing that destroys this party is damper. So damper is simply it releases the energy, it dissipates the energy, maybe in the form of, because let's say in case of nut and bolt, it will keep on vibrating, so there will be resistance at the nut and bolt, and that energy will be released in the form of heat. If not the nut and bolt, then that energy will be released in opposing the air flow. So naturally, all of these things are acting like a damper. So obviously that's a very simple example of what how the mechanical vibrating system works. So they have different elements now, and you should now, the purpose of this explanation was that you should, whenever you encounter a mechanical system, you should be able to understand what each component will be doing in your case, and that will help you to formulate or to make a model or the mathematical model of that system. So that was just a brief introduction of what the elements of the mechanical vibrations are. Now the next is, all of these elements can exist in different forms in the vibrating system. So let's say, starting with the first one, I will just starting with the first one. Now we are coming towards the mathematical side of this one. In a vibrating system, uh, so the mass, it can exist as a translational mass, like this one. It is moving in the same direction. That's a translation mass. So we know that the velocity is this one, and a is equals to uh, change in velocity over time, or actually it's basically dv over dt. And since velocity itself is, if it's x coordinate, velocity itself is x over time, so we can write it as d square over dt square of x, or we can write it as x double dot. I hope you are aware with this double dot and single dot. So single dot means first derivative, double dot means double derivative. So you can write acceleration as this one. And so in that case, the inertia will be F is equals to ma, or you can write it as mx double dot, right? Or the this mass can exist as a rotational mass. Let's say, so you have a disk like this one. It's a very poor looking disk, so I apologize for that one. And you start rotating that disk to apply the rotational force, so the inertia of that disk will try to maintain its original position. So here it will be represented as torque, that's equals to moment of inertia into the alpha, where alpha is the angular acceleration. So alpha is d omega over dt, and we know omega is equals to angular acceleration, that is d theta over t. So we can write it as d square over dt square of theta, or we can write it as the angular acceleration as theta double dot, in case we are dealing with the system that is rotating at certain angle. So this can be done for the cylinder, this can be done for the hollow cylinder or the tube or the disc. So all of them comes in this one. Now the second element is the spring elements. If you write it as, so again, spring can be a translational spring, It can exist as a translational spring. Let's say you have a spring and here you apply the force. So we know F equals to, let's say this was the original position of a spring X. So F equals to Kx, whatever you apply. And then the another thing is spring can exist in the form of the rotation. Let's a translational spring again. Other one is rotational, or more appropriately, this for the spring case it's called as a torsional spring. Torsional spring. So here you can write it as torque is equals to k theta, where theta is the, let's say you're dealing with a rod attached to a wall and you're rotating it at an angle of theta. So that's a torque you applied, torsion you created onto the this rod attached to a wall. So this is how you can classify these one. Other one are the third element is a damper, and it causes the, I will write here. So damper can also, it's called B into damping coefficient, so which is simply the velocity one. So you can call it at t equals to b theta dot, or uh, f equals to b x dot. That's a damping force one. So that's the basic introduction of the spring, the elements of mechanical vibrating system, and we will see these systems in detail. So here are some examples of the vibrating system. The second thing before discussing these figures is the degree of freedom. So I hope you guys are aware of what the degree of freedom is. So sorry, it's converting into the shapes. Degree of freedom. It's like a number of independent coordinates that exist in for a system. What does that mean? I gave you a very simple example of this mass spring damper system. And if we apply the force here, what are the number of independent coordinates that the system will move along? So let's say if this is x, this is y, this is z. So system here we can see can only move along the x-axis, right? So the number of you can call it end of number of degree of freedom is 1, and number of independent coordinate is also 1, that is x. But come just have a look at this one. So in this system we can apply force here, and this mass will vibrate independently of this one, right? Because there's a spring connection between them. Not necessarily that if this mass moves 10 centimeter, so this will also move 10 centimeter. It's not necessary. So it does have the 1 degree of freedom, but it has two independent coordinates. So the number of degree of freedom is again 1. It can move only along x-axis, but number of independent coordinates in this case are 2, right? Then you can check out this one. So again it can, this both of these discs can be rotated independently. The disc 1 doesn't depend on disc 2. There will be some force transfer, but you can rotate this one in this direction, other one in this direction. It's absolutely possible. Although the number of degree of freedom is 1 again, because they both are along the rotational plane, but the number of independent coordinates are 2, that is theta 1 and theta 2. you have another example of this one. So here the system have movement in this direction as well as along this direction too. So it does have 2 degree of freedom. It can move along x-axis, it can move along this theta, and it has 2 independent coordinates as well. So your number of independent coordinates determines how many mathematical equation you will have at the end of the mathematical model. So before start solving any mechanical vibrating system, just try to first confirm like how many independent coordinates you have. This will help you to check out like either you are driving a correct mathematical model. Otherwise you may lose your path while solving, and it will waste a lot of your time. So this is the first thing you should do whenever any system you encounter any system. Just try to find out the number of degree of freedoms and number of independent coordinates. Now we have discussed the what the mechanical vibrations are. We have seen what are the elements that define the mechanical vibrating system. So how we are going to define any system in terms of these elements, which are the mass, which represent inertia, second is spring, which represents the stiffness of the system, and the third is damper, which represents the damping of the system, or you can call it in case of fluid is viscosity. Then we discuss the degree of freedom, which is the, you can call it the minimum number of independent coordinates that is required to represent the system completely. That is the degree of freedom. The last one is what are the different classification of vibrating system. So whenever, so that you know, whenever you encounter a mechanical vibrating system, you know what are the different elements that are part of it, what are the degree of freedom, and which category does it lie in, so that you can apply the appropriate mathematical modeling technique. And once you find the mathematical model, you can apply the suitable solution technique, right? So in the initial lectures, our main focus would be to first to be able to identify the system, its degree of freedom, its independent coordinates, and to be able to formulate the mathematical model. And as soon as we reach towards the mid semester, our main focus would be that perform the solution of those mathematical model using different techniques based on our what do we aim there. And towards the last, uh, we will invest some time into the continuous vibration. So whatever we are studying here is called a discrete system. It's called a discrete system, and we will see that in future. So how do we classify the vibrating system, the classification of vibrating system? So if we jump here, then the fourth part of our lecture here. So the classification of vibrating system. Sorry. So, a vibrating system can be classified based on how the force is being applied. It can be classified, as I told you, as we have discussed slightly, based on damping, whether either the damping exists or not. It can be classified based on linear or the non-linear behavior. We have discussed this in the system dynamics as well. It can be classified based on whether the vibration that is being generated, there's a regular pattern or they're random. So these are four bases of the classification of the vibrating systems. The first one is that is called as free and force vibration. That's called the free and the force vibration. So there are two ways to classify this one. What is free vibration? I will just draw the figures and then let you know. So let's say you have a mass spring damper system, and if you apply the force at t equals to 0, means from the time you start observing the system, just before that you apply the excitation initially, and then you remove it, and then your clock starts and you start observing what's happening with my system. So you apply the force at t equals to 0, and then you remove it and then let the system vibrate on its own. So maybe system will vibrate like a pendulum with the damping. So it will go from this extreme position to the other one, then it will go back to the first one, then slowly and progressively it will start losing its energy because of damper, and ultimately it will come to rest at the mean position. The same thing with the free vibrating system. If you apply the initial excitation, it will start vibrating to extreme positions and then go back to the this position, and it will keep on vibrating between these two edges until it slowly starts to lose the energy because of existence of damper, and ultimately it will come to rest at the mean position. That's the free vibration. So there's the force was not involved throughout the time. Force was just there as an initial excitation. Force is just an initial excitation. You can call it applied force. Applied force is just an initial excitation. So it's not like the force is continuously being applied throughout the time. While now you must have guessed what is a force vibration. So force is applied. The system is subjected to the external force throughout the vibrating time or the time you are observing. So let's say this is a system with a spring mass damper system, and now you are applying the force. Sorry, you are applying the force from, let's say, t equals to 0 to 10 seconds. So you're continuously applying force for 10 seconds, and that force can be a step force, it can be a ramp force, it can be a sinusoidal force. So we'll see what these are. So that force can be in the form of step force. Step force means system was at 0, there was no force, and suddenly for 1 second uh, we applied the force of 10 and maintained that force. That's kind of, it looks like a step, like your stairs. What's the ramp force? System was at 0 force, and then at time equals to 1 to time equals to 10 second, you slowly and progressively increase the force to 10 or whatever the force was, and then you maintain it or you remove it, whatever we are doing. That's a ramp force, and we'll discuss this in detail. And sinusoidal force, like you are applying force in a sinusoidal form. So you have the mean position as 0, let's say, and you're applying force 10 and negative 10, then positive 10, then negative 10 at certain frequency. Obviously you need to know the frequency of your sinusoidal force. So that is a force vibration, which we are not, the force is not just an initial excitation, rather we are applying force for some time and observing the behavior of our system. So that is a force vibration. Second way is to classify that one is really easy. We have already discussed that one. Damp and undamped system. So again, we did when there's a damper present there in a system, that's called a damped system. When there's no damper there, that's called undamped system. What's the difference between them? In undamped system, it's, you can call it a theoretical system. It doesn't exist in real world, but we do model a lot of real world system as an undamped system just to study the ideal behavior and to avoid complexity in our calculation if damping is really low compared to the force. Obviously you have to have a smart guess, like is the damping large enough that it will affect your results compared to the force, compared to the inertia of the system. Maybe inertia is too big and your damping is really small, so obviously in that case damping is not going to affect your results. So but in reality damping is always present. So undamped is like a theoretical scenario where there's no damping. So when there's no damping, ideally system should keep on vibrating, keep on vibrating. Because this is what happened, that the spring is transferring energy to mass is transferring energy back to the spring, and they will keep on dance like this, and there's no energy loss. So if there's energy loss, it means there's some damping either in the form of heat, in the form of pressure, or viscosity. We don't know. So that's an undamped system. While the dam system, we know there's a damping involved. It can exist in the form of air, it can exist in the form of fluid. Like a hydraulic system, it can exist in the form of heat, like resistance, friction, in your the brake disc of your car. So this is what happened in your car when your car is moving at high speed. You apply a brake, so that there's a brake disc that comes in contact with your car wheel, and that creates a resistance. And so whatever energy your car has in the form of kinetic energy in the inertia of the body, that energy is being dissipated through heat at the brake disc. So this is what happening. That's also kind of damping of your car. Then another way, I think we don't need to discuss more. That's enough. Then another one is linear and the non-linear system. Non-linear vibrating system. So we have discussed this in the previous lecture too. If the mass and the spring and the damper are behaving linearly, we call them to be linear system or the linear vibrating system. If, however, any of these basic components behave in a non-linear way, we'll call that to be a non-linear vibration system, and they will be modeled using the higher order equations, maybe second order, third order equations, and they will have the solution up accordingly based on the number of order you are using for your differential equation. So let's say spring, we know that F is equals to kx. So spring should always, for every 1 Newton force, spring should, let's say, go 1 centimeter or 1 meter. For second Newton force, spring should extend by 2 meters and so on and so forth. But if your spring is behaving like this, so it is clearly a non-linear behavior. There is something involved. It means your system is not linear elastic. Maybe your system is, you can say, hyper elastic, or maybe your system is viscoelastic, right? So in that case, you will have the different types of technique to handle these kind of linear equations. So like what if I give example of my PhD research. So I was dealing with the vibration of nucleus. uh, so in my PhD program, I was working on the vibration of a nucleus. A human cell has a nucleus and filled with the cytoplasm. So you have a nucleus here, and then you have the cell wall. You guys must have studied some biology in your high school. Those who have studied, you have cell wall, and this region is filled with a fluid called cytoplasm. So that cytoplasm is basically viscoelastic medium. It's kind of viscous fluid. So I was dealing with the vibration of new. If you apply sound waves onto this nucleus, so this nucleus will vibrate in the cytoplasm. So because of this, cytoplasm is viscoelastic, so it means it has elasticity, it has viscosity. So the nucleus will have some spring effect, it will have some damping effect in the cytoplasm on both sides, like this one. So nucleus will keep on vibrating like this one, and the cytoplasm will resist the vibration of that one. So this is how you can model, and because that's a viscoelastic medium, so it means there's no F equals to kx. So there was much more complex equation to model the human biological cell. So this is how we can even apply the mechanical vibration principles onto a system like a human body. So you can deal with the vibrations of your internal body structures, maybe the cells or the muscles. Many of the therapeutic technique is based on vibrating your muscles to give relief to the patient. So maybe you can model your vibration of the muscles, how they will behave if you apply this frequency and amplitude of vibration. So don't just restrict your horizon to just pure mechanical car or aeroplane or the machine. It can be applied in a whole lot of systems. Maybe some chemical compound which has, let's say, the some atoms are bonded to the other one with some elastic bond. so that bonding force has some elasticity in it. It can be measured as well. So there's a technique that is used called atomic force microscopy. So you can use atomic force microscope. It has a cantilever like this one, and you can bring down cantilever and touch the atom and apply force onto a single atom, and that atom will resist the cantilevers. This is how you can make a stress strain curve or the force displacement curve of that atom, and this is how you know what is the elasticity of the bonding that atom has with the surrounding atoms. So even like this fundamentals of mechanical vibration, they are applied not just in mechanical system, they're applied in chemistry, they're applied in biology, biomedical, and whole lot of other applications. So just keep your horizon big and try to think out of the box, not just in terms of pure mechanical, but just try to think of in the mechanical system, the fluid system, electrical, thermal, and all of these cases. So that was just like a side note how you can apply these things and what do we mean by linear and non-linear. Maybe I can just leave this as it is. Okay, and that is a linear and non-linear vibration. Now the fourth one, the fourth basis how you can classify your vibrating system is either it's a random vibration or it's deterministic. That's called deterministic. Deterministic. So if the magnitude of the excitation force acting the magnitude of excitation force is known at any given point, at any given point, you can say that's called a deterministic vibration. So you know what amount of force is being applied, is acting onto the system. That's called a deterministic system. And one is called random vibration, where you don't know what kind of force or what is the magnitude of force that is being acting onto the system. What are the examples of that one? So let's say you are what you can say, let's say you have a washing machine. Maybe you have seen a front load washing machine where you put clothes from the front. So there it rotates at a very high speed. Because of that, there's a vibration in the system, and so it vibrates. So what they do, they put a rubber pad to absorb the vibrations. So based on the rotational speed, omega, you can find out the force, the centrifugal force that is being generated. So what is the force that is causing the vibration? But there are a lot of chances. Maybe you are flying. Sorry, it would be a very weird looking plane. Maybe you are flying up in a plane, and that plane is the for some time the everything was fine. Now you have some turbulence along the path of the plane. So because of that, the plane will experience, you can say plane will shutter, plane will vibrate violently, and that will be a random vibration. Plane will go like this, like this, like this, like this. So there's no regular pattern, and you don't know what is the amount of force that is acting onto the plane. So that's called a random vibration. So there are techniques to evaluate the random vibrations too, and there are techniques which we are going to deal with to evaluate the deterministic vibration. So in our course, we are mostly focused on deterministic vibration. We are not going to focus on the random vibration. There are some statistical technique to evaluate the random vibration based on the data we capture. So, but even we do have some testing of systems which may be subjected to random vibration in their application. So that is the was a brief introduction of the mechanical vibration and what what are those, what are the different elements of the mechanical vibration, what are the classification. These were the all like a toolbox for you that will be helpful for you to perform or to model the mechanical vibrating system, to perform the solution of that vibrating system. So just have a look and just listen on this lecture, and I will share some notes. Just have a look at it and keep this lecture with you all the time whenever you're studying the mechanical vibration, so that you can easily understand what kind of system you're dealing with and how you should approach any system. So that was all for this lecture. Next lecture I'm going to be uploading again very soon, and in that lecture we are going to formally start the solutions of the vibrating system. So what we are going to do, we are going to study single order systems, or you can call it single degree of freedom system. Single degree of freedom. Then we will deal with the second degree of freedom system, and then we will deal with the multi degree of freedom system. So that's called the S-DOF. That's also called the you can say SU-DOF or SA-DOF. Just SA-DOF, sorry. And that's called the M-DOF system, multi-degree of freedom. So we'll start with this one and gain some momentum while calculating, performing the modeling of this one, and then we'll move toward the multi-degree of freedom. So our main focus, these are our focus in terms of system, but our in terms of how to approach the vibrating analysis of the vibrating system. Again, it has the same approach. The first one will be understanding the system. Second one would be mathematical modeling, and the third one will be derivation of governing equation or solution of equation, solution of system, and the third one will be the simulation, you can say. So in the initial lecture, we'll focus on mathematical model, how we can drive a mathematical model of different kind of system. So once you get proficiency in this one, then we'll move toward the solution of mathematical model. So we will see different techniques of mathematical model, and then we will see different techniques of performing the solution of mathematical model, and then we will see the different techniques of doing the simulation of mathematical that system. So this is how we will proceed. So I hope so this lecture was informative for you. So from the next lecture we are going to formally start all of this solution, and in this week I will upload two more lectures to cover up the last week. And I hope, should you have any question, you can just approach me directly on my email ID or on WhatsApp. Thank you very much.